past probably 2.5 years, I've always kind of had this little projects that I've been playing around with, looking at how we can use AI and learn about AI for being able to work with games. And Eve's going to kind of round this off. We're talking about some more real world examples of kind of where these ideas are actually used within the game industry to be able to help developers to leverage the power that we've got in the Microsoft Azure data centers to be able to train AIs that are actually used in production games. So what I'm going to be talking about is genetic algorithms, exploding rockets, neural networks, and self-driving game AI. A bit about myself. I describe myself as a developer, trainer, mentor, and evangelist. I love writing code. I'm happiest working in Visual Studio. I also deliver training courses, mostly on cloud and AI technologies. And these are classroom courses when that's possible, remote courses. And then I'll also work for Pluralsight, recording courses for them. I work in Stockholm, Sweden. I'm originally from the north of England, but I've been in Sweden for the past 22 years for a company called Active Solution. And we specialize in building cloud-based applications on the Azure platform for customers. I hold the Azure MVP award. I've been an MVP since 2005 for BizTalk Server, then integration. And the kind of work that's kind of driven my passion for being an MVP is being involved in the community. I've been involved with building labs for the Global Azure and Global AI boot camps, and then also organising Cloudburst and AI Burst conferences in Sweden. I do YouTube, and I've got a YouTube channel here. Some of my demos are out on YouTube if you do want to check those out. I'm very inspired with AI. I was teaching a course, this is probably going back 2 or 3 years, in Kista, just north of Stockholm, and they had an AI day, and this thing was basically bumbling around the streets, cleaning up. It's an autonomous street cleaner. And they also had this is a delivery truck without a driver. And I was really fascinated by, what makes these things work? How do these things work? What's the technology that's behind that? And that kind of helped to fire my interest looking at AI and machine learning. So I'm going to start off talking about a fairly basic algorithm called the genetic algorithm. And it's a way of being able to kind of model evolution and the evolutionary processes that take place in nature, but be able to do that with a computer algorithm. Now, both in natural evolution and also in the genetic algorithm, we start with an initial population. And the initial population, it could be, players in a game. It could be, cars that are going to drive. It could be, Connect 4 players, basically anything that's going to be competing and trying to be able to score running in a particular environment. And with this initial population, we perform some type of evaluation. So if it's something like a shoot 'em up game, you'd look at how many points were scored, how many ships did you shoot. If it's a driving game, maybe how fast did you drive without crashing, and that will be able to give us some kind of numeric score to be able to rate this initial population. The initial population is usually created with random numbers. So they will basically all perform very, very poorly at the given task. However, some of them will perform slightly less poorly than others. And then what we can do is we can select the top performers out of this random generation. And we can do a couple of things with that. We can do something called crossover. And again, this is taken from natural selection. When animals or humans breed, you basically get some genes from one parent, some genes from another parent, and that goes on to form the next generation. And we kind of simulate that in the genetic algorithm by taking certain numbers and values from each of the actual population and combining those together. We also have something called mutation, and this is again coming from nature. You may have heard of a genetic mutation being a chance. We've got random numbers here, so we probably haven't got the optimal random numbers to be able to perform best at the specific task. So mutation is just randomly flipping a few of the numbers or generating new random numbers. So maybe you'll say, okay, 2% of the numbers that make up that particular member of the population, we'll just replace them with new random numbers. And then we go through the evolution stage. And that's basically the first generation. And we'll run around multiple generations of this until we can basically get something that is basically evolving and performing at a particular task. So I'm a big fan of what Elon Musk is doing with SpaceX. I try and watch the SpaceX launches live, and I was really impressed by the way that they're being able to, bring these rockets down and land them on the landing pad. The amount of technology and work and physics and science and engineering that goes into to make that happen is really fascinating. It's a real world project. It's millions and billions of dollars are being spent doing this. So I decided to do a kind of simulation of this, and this was one of the simplest things you can do with a genetic algorithm. I came up with this idea of something called a thrust vector table. So as the rocket is landing, you have the actual altitude of the rocket, which is an input that we can put into the algorithm. And what the algorithm is going to decide is how much thrust we should use for the engine based on the altitude. So we have an initial burn here, and then we decrease and maybe increase here. And as the rocket comes down to the ground, we have a final burn to be able to actually, make sure the rocket doesn't crash and lands gracefully. However, there's a fixed amount of fuel in the rockets. And so if you burn too much up here at a high altitude in the high burn, you're going to run out of fuel and you won't have any fuel left to be able to do the final burn. Also, as you burn off fuel, the rocket becomes lighter. So that affects the physics and dynamics of this rocket. So there is going to be an optimal, what we call a thrust vector table, to be able to land rockets successfully. And we're going to look at using a genetic algorithm to be able to see if we can determine what that value is going to be. So back to the genetic algorithm, we're going to generate 25 rockets, and the thrust vector tables that we generate in these rockets are going to be completely random, which basically means pretty much when we evaluate it, when we simulate the rocket landings, all the rockets are going to crash and they're going to explode. However, some of the rockets are going to crash slower than the other rockets, and that's something that we want to perform for selection. The rockets with the lowest landing velocity are going to be selected, and then we're going to perform the crossover to generate 25 new thrust vector tables based on combining the thrust vector tables of the most successful rockets. We'll then throw in a few random numbers just so we can, put some variety into the population, and we'll do the evolution again and see if we can get a better result here. So, first demo, landing rockets with a genetic algorithm. What could possibly go wrong? So I'm going to bring up Unity here. I've got this thing running in Unity. I like Unity. It's got a nice physics engine. You can do nice things with graphics. It's also, you can use C# as the programming language in Visual Studio. So it's pretty nice to work with, fairly easy to work with. So if I run this simulation, we're going to get 20. They will probably all explode and crash into the ground, but one of them I think landed with a lower velocity. It's looking like that rocket that was closest to us on my landing with a slower velocity. So what it's trying to do is to propagate these values and hopefully as in velocity. One of the challenges here is this is random. We could sit here for 20 minutes. None of them land successfully, but hopefully the luck will be on our side. I have done it a few times. Get a successful rocket, but if not, I'll just leave it cooking in the background and we'll hopefully see it. I'm hoping that one is going to land. Elon Musk had quite a lot of explosions before landing his first successful rockets. But he's not using random numbers, I don't think, when he sets these things up. I thought there was some progress there. They did look to be slowing down a bit. No, this isn't working as I planned. Yeah, I'm going to leave it a couple more times and then they do seem to be landing slower. What I'm going to do is to just restart it. Because it's initialized with random numbers, you get a completely different set of random numbers and it might be a bit more successful. It seems like there's a lot more variety in this. Okay, if they don't land this time, I'm going to drop it on another screen and I will drop back to it. This looks like it would have been a very expensive demo in reality, so I'm going to drag that off. Well, I did mention that I was going to. That was true. Okay, so moving on, I'm going to look at in neural networks into the concept of working with a genetic algorithm. Now, pretty basic in that there wasn't that much we could control. The only thing we were controlling was the thrust, velocity, and there's not that much sort of variation that we can put into the algorithms. However, something like driving a car, a lot more complex. There's a lot more variables that we have to deal with. So, looking at working. The idea is that neural networks are made up of these neurons. We have inputs to the neurons, which typically have between, say, -1 and +1. And we also have something called a bias, which set the appropriate value. And within the neural network, the formula looks like this. By the biases, the inputs by the weights, and then we add the bias, and that gives us function, which is going to keep the numbers, the output 0 and 1. So sigmoid is quite a classic one to be able to use, and give an output of 0.94. Okay, so looking at a neural network, combining a number of neurons together to be able to form a network of layers. As equations become more complex and as we're trying to solve more complex problems, then we want to be able to processing power, and combining these neurons together allows us to solve more complex equations. So traditionally, I was just wondering if you hear me okay? Okay. So traditionally, this is done with character recognition, or OCR. We do something like running data sets through a neural network and doing something called back propagation. We basically adjust these weights and biases by making it more. It's based on various algorithms that we have called gradient descent. However, when working with something like an evolutionary problem, the known answer to the actual questions that we're focusing on. So if the car is going to itself, then we don't actually know what the optimal path is. So in this case, we use a genetic algorithm to be able to set completely random values for the weights and the bias, and then we use the evolution to modify these weights and bias and get a more desired outcome. This is used with Atari. One of the scenarios was building an AI that could play Atari games. So if you bitmap screen, and we take the pixels off that bitmap screen, and those are going to be the inputs. The output from the neural network is going to be so the output is fed into the controller, and we can evaluate how well each AI is performing by looking at the actual score. So the more points that you score, the better the algorithm will be performing. And we can use the same with the genetic algorithm to be able to do that selection, the mutations, the crossovers, multiple generations. So when they've been testing this at OpenAI, they have actually developed AI better than humans can play them, and be able to adapt to be able to play any Atari game. So it's making a series of inputs, and they're judged by the score that they're making. So what inspired me to get involved with self-driving cars was who'd done some great webcasts on working with GTA and building a neural network reasonably well at a GTA and be able to drive around. I think it was several months and several weeks that it took for the algorithm to train, and he had it running on a live stream. We could just see learning to drive, and it was actually driving pretty well in GTA, at least better than I could. The other thing that the Syntax has done is looking at working with building AIs to play Starcraft. Again, genetic algorithms and using the evolutionary learning and using neural networks. The thing I like about AI is you can do stuff at home, and you can also see it done. Because when DeepMind built an AI that was going to be playing this is the screenshots from their AI analyzing the maps to looking at this one here. we can see that we've got this basically looks very similar to what they were actually building in those scenarios there. To look at self-driving cars, I actually do have a demo that I'm going to spin up, and hopefully this will be more successful and burning. And I'll see if I can bring this demo up in Visual Studio. And what this one is going to do, we've got a generation of 50 cars. Now, none of these cars know how to drive. What we're seeing here is the performing car. And what we're going to score the cars on is how far they can drive before they crash into the... See that one crashed. So generation 1 got 455 pixels, and we've got running now. And that seems to be the best performer in generation 2. And as we go through these generations, we're doing the same process. We're doing the crossover. And hopefully, after a few generations, these AIs should be able to evolve to drive. This one is basically navigating around this corner. It seems to have got a lot further than previous ones. So this one is the distance. It may actually get all the way around the track, this one. And the inputs I'm using for these are distance sensors. So I've coded some distance sensors which tells it how far it is to the actual barriers of the track. And it's using those network to decide if it's going to turn left or right, or if it's going to do the accelerator and the brakes. So it's kind of looking to drive around the track. It did almost crash there. But what will happen is this neural network will then be replicated out and used for other. Hopefully what should happen after a few generations is we should see more cars driving around the track. There's also a certain amount of time, then it basically stops. He's basically going to get better points and be able to result in a higher score. So can we start with cooking? Just drop down because it does take a while for the timer to of these cars actually running. The rockets are still crashing, by the way, on a show of those rockets landing successfully, but we've still got a few minutes left. So this same AI in the global AI bootcamp in the actual lab. As in the global Azure bootcamp, I've been working with this racing game where the running in Microsoft Azure, and what we're doing is basically, people from can compete, and they can basically see who's getting the highest score. What I did for the global AI, AI into the game. So as I've tested within the 2D simulation into a 3D world, and basically took exactly the same neural network. So we measure up to the side of the track from the left and the right front, and then we've got these sensors at 45 game units or meters or whatever, how far it is to the actual barriers. And we were running various the generic algorithm to set the weights in the neural network. We've got the sensor data coming into the controls as being the output for the neural network. Okay, it's the same type of thing. We start with 50 cars, as I was doing in my little Windows application. Each car is the cars with the AIs that perform best are going to be selected. We then can perform our crossover, generate 50 new AIs, and that's going to result in the actual new. What I was doing was basically building up these where we've got the distance sensors providing the input, the output is out to the throttle and the brakes, and then out to the steering to be able to control. There's a few interesting things that happened when I was running this demo. This is basically testing evolution. See here is the actual generation number of the name. So this is generation 34, 930 meters along the track. And then the AI in basically at 733 meters. It was basically not pressing turn that particular area in the track. Now, what I was doing, I was scoring the cars distance travelled and also the time. And so the cars that drove the fastest this turn were basically coming out as having the top score. That and crashing at this corner would basically get you a higher score and stay with. And you can get these types of scenarios happening. These types of genetic algorithms, and you can basically restart it as my rockets haven't successfully navigated the map. Another thing that happened that was a bit strange is something called a false minimum. So as I was running these evolutions, ended up like this. So if I drop on the actual video, start it. One of the generations, the car that got the furthest had basically turned around and drove backwards, and that basically. So that meant that the genes that were being replicated were basically from this car that was the population. So as this was evolving, you can see it's running on about generation. I think they've had about 27 generations. The cars are basically driving further and further and further backwards. They basically evolved to be able to become proficient at driving backwards, which isn't, but it's not really what we want. And with evolutionary scenarios, you can basically get these types. Many scenarios. Another example was one of these games. Somebody was working with an evolutionary AI, and what happened was that the AI figured out that if you press the pause button, then you'd be able to hours because the game would just be paused. So the evolutionary AI just said, I can survive the longest in this game by pressing pause, and that was basically its to survival. So we actually ran this in the Global AI Bootcamp, and this that's dropping up. The interesting thing is we ran it when it was the Global AI Bootcamp as artificial intelligence in the game versus human drivers. So you could choose when you started the game, you could say, I want an AI that's evolve and run on your machine. So you can see that Nigeria evolved an AI. I've used the Terminator skulls for the AIs, and I've used the Stig skulls, these white helmets for the human drivers. So you can see that within the top 10 position, 7 were basically AIs that had evolved and are able to compete very well with in this driving game. I then moved on to look at Forza. One of my favourite racing games. I play Forza quite a lot, and what I was doing is looking at the input frame and being able to the input frame. So instead of getting lots of artifacts, we've basically got this thing here, which is and this is taken from this cyan color in the driving line. And what I was able to do is to build a similar neural network that was using the kind of driver line to decide how to move the steering wheel. If you take a quick look at this video, this is basically showing about 48 hours of evolution for this AI. It started out basically not knowing much, it was crashing a lot, and then it figured out that it could actually follow the driving line, and when it got to a right-hand bend, it would turn left and drive out into the field. But as it evolved, it was actually figuring out the correct way to drive. I chose an Italian car for this. I think it's a Lamborghini Huracan or something like that. And basically, it did actually evolve over 48 hours to be able to kind of navigate these small bends within the track. This is actually the Top Gear test track, I think, in the UK somewhere. However, I never actually got it to get round the sharp corner that you can see there. It was never evolving. It just kind of got stuck at that moment. It was consuming a lot of time. Actually, sat running on my laptop 24/7, just being able to do this at this particular evolution. It may have been possible to get it to evolve better if I'd have played around with the algorithm a bit more. But time is always an issue here, and I kind of think it's quite nicely demonstrated that you can apply evolutionary learning to simple scenarios like that. So going further with this, if you would like to go further with this, One thing you could look at is using Azure Custom Vision. You can train models to be able to react to other cars. There's some great content out on YouTube. I've put out some of the stuff that I've been working on with AI, both in Python and C# using the Azure technologies. 3 Blue, 1 Brown on YouTube has some great videos. We'll try and include these in the actual links on YouTube for this session. I also recommend Jabril's. He's done some great YouTube videos on the Forest AI, talking about his experiments with evolutionary learning, and the CentDex stuff looking at working with Python plays GTA. If you'd like to look at self-driving AIs, Carla provides a simulation environment where you can run AIs in a 3D environment and you can program that in Python. So that's definitely worth looking at. So thanks very much. I'm going to hand over to Eve now, who's going to basically take these ideas and put them into production, showing how they've been used in real-world games.
Thank you, Alan. And there we go. So I also want to say a big thank you. For the team to making AI and machine learning conference. So it is really cool to be here as a speaker. And Alan, thank you a lot again for the introduction. It has been really inspiring. So I am also really excited to share some insights and offer a first glimpse in Ninja's theories game. The Bleeding Edge is allowing Microsoft Research to drive research into artificial agents that learn to collaborate with humans. Microsoft made an amazing history in machine learning and artificial intelligence, applying machine learning services, such as for the suggestions made in Office services. So the approach of reinforcement learning became really popular in the recent years, since these game agents perform complex tasks really well and causing real breakthroughs in the field. And there are many use cases in the world which uses this technology in the areas such as robotics, chemistry, education, and a lot more. So I am Eve Pardy, consultant at Avanade. I am also an AI MVP since 2020. And since that, I am involved in different community activities. For example, I am one of the board members of Global AI Community and co-owner of AI42. AI42 is a series of lectures for those who would like to become data scientists or AI engineers. And we aim to take attendees all the way from complete beginner to getting enough knowledge to be able to build their own model. I also write articles and often speak about my investigations and projects at different meetups, conferences, or other community events. And my aim is to save lives and support humanity with AI and data. And it is also really important to make people feel safe while using intelligent applications and also make developers understand how they should control their solutions. I would be really happy to answer all your questions after the session. But if you have more or you're stuck somewhere while you're trying out the projects we show you today, feel free to reach out to us. You can find me on LinkedIn, Twitter, and Facebook too, but you might as well write me an email. So the cool thing about a gaming situation is that the behavior of the agent is trained under the pressure of the game. Like, think of a character or a bot in a game. It has to understand the state of the game, where are the players, the objectives, and then based on this observation, it should make a decision. So, for example, it could learn what to do when it's being attacked or how to behave in order to reach a specific goal. And Microsoft proudly announced the preview of reinforcement learning on Azure Machine Learning at Build 2020. And the new reinforcement learning support in Azure Machine Learning services provides scalability while training to CPU or GPU virtual machines with machine learning compute clusters that can automatically provision, manage, and scale these virtual machines. You can also use either single agent or multi-agent reinforcement learning for your training scenarios. You can use different gaming environments like the OpenAI Gym. You can also build your models with TensorFlow and PyTorch deep learning frameworks, and it supports ONNX too. Then you can also track your experiment and monitor the runs. And Azure provides numerous AI solutions to build, run, and grow your games. So go ahead and accelerate your games with AI and machine learning to provide more realistic worlds and challenges for your players. And to get started with reinforcement learning, you can go ahead and check out the sample notebooks to train an agent. And for example, you can use this one to navigate a lava maze in Minecraft using Azure Machine Learning, which uses single agent reinforcement learning. So the goal of this agent is to reach the blue tiles while navigating through this maze by walking only on solid tiles. And the agent might fall into the lava, in which case it has to start it over. And since the maps are generated randomly, this agent also has to learn how to generalize and adapt. So I'm going to try to start this up. Cool. So non-player characters are the heart and soul of many video games. And new AI technology lets developers create characters that act organically and respond naturally to the player. And the goal of Project Paidia team of Microsoft Research, in collaboration with game developer Ninja Theory, is to democratize state-of-the-art reinforcement learning techniques for any developer through Azure Machine Learning, and to provide access to training infrastructure and easy integration tools. So by this, make developers able to apply reinforcement learning while building exciting games for their players. And when it comes to video games, reinforcement learning agents have typically been trained to win against human opponents, just like the famous chess agent, you know. But what if we taught them to collaborate with human players instead? So the game I want to show you is designed to rapidly test this collaboration between two players. So I'm going to head over to this place. So in this situation, we are locked in a room on a spaceship, and we have to collaborate. And there is one white agent, that is me, and the other one is the blue agent, that is the agent that is trained. This is a reinforcement learning agent. So while one player keeps the switch active, the other player can go and press the buttons to open the door and escape the game. So it has to fall in, and now I open the other door. There. Cool, and so the door opens, so I can get out. Cool, but what if I decide that, okay, I'm going to go ahead and take care of this button. To see, the reinforcement learning agent is going to go and switch the buttons then. And if I come here, okay, now I was too slow to show you that, but you know, if I change my mind, the agent also changes his mind. So no, I'm going to take care of this, thank you. Okay, now I do that. Oh, it's all right, cool. So we sort of work together, and we have to collaborate and get out of this room. And this agent is trained by putting it in a wide range of different game situations, randomizing the position of the agent. So it has gathered a lot of data of how it can interact in those different scenarios. So in this session, we'll look into how to train a multi-agent reinforcement learning scenario and use the following situation. There we have the blue circles. These are the agents, and they start spreading around and observe their environment while finding the landmarks that are shown as black circles. So they get rewarded if they find the landmarks without overlapping while spreading around. And for this, we use OpenAI Gem's particle environment within Azure Machine Learning. So let's take a look into an example of how multiple agents can be trained with Azure Machine Learning in a simple gaming environment. So I'm going to switch over to the Azure portal. And to see this, you will need an Azure subscription. And then you also need a resource group and a machine learning workspace with a computation cluster in the resource group. So if you want to create a new machine learning studio, you just go ahead, say create resource, and say machine learning. You click create. And then first you need to provide a resource group. You can also create a new one. A resource group is a container that holds related resources for an Azure solution. And you decide how you want to allocate resources to resource groups based on what makes sense for you. But generally, you can add resources that share the same lifecycle, so you can easily deploy, update, and delete them as a group. Then you also define a name for your workspace, and then a storage account, a key vault, and an app insight is also generated for you. But a computer registry should be generated with the workspace as well, because a container registry is used to register Docker images used in training and deployment. So to minimize cost, a new Azure Container Registry resource is created only after you build your first image. So when this resource is deployed, then you can navigate to the overview of the resource and you can start up the workspace from here. And this is the view you first see when you launch your workspace. You can choose to work with notebooks to write your own code and build your own models and experiments. You can choose to work with automated machine learning, where you can automatically train and tune your models, and you also get the best fitting algorithm for your scenario. And then the designer is a drag and drop interface with which you can prepare your data, train, and then deploy your model. So we need to also create a compute, and you can do that by going to the compute menu and click new, and you give it a name, and then you want to choose whether you want to go with CPU or GPU. For this one, it's a good idea to go with GPU, and you can choose from the one that is already available for you, or if you go with CPU, you can use this one as well. All right, so I'm not going to create a new one because I have one already. So I'm just going back to my notebooks. So from the home page, you can start up the notebooks like this. And this might look familiar for you if you have coded with Python before, where you possibly use this Jupyter IPython notebooks, which also have similar folder structure, and it also has this this line-by-line coding structure as well. So we first need to create a files folder and place there all the files that you can find in either this GitHub folder, which is mine, or you can find it in the original one that is in Azure Machine Learning Notebooks, how to use Azure, etc. But yeah, it's faster to just go to my repository because it's easier to remember. So when you are ready, we can move back to our main folder, and I already created a notebook here where we can start coding. So you see, you can only run code in here if you connect it to a compute. So we just go ahead from here. You're welcome to install and update all the environment, but all the things that you would use in this project is already installed for us. So all the libraries that you would need is already here. And we can also return the SDK version of Azure Machine Learning. It's quite handy when you need to do some debugging. It is also a good idea to define which Azure tenant you want to use. So you can specify it with the use of this kind of code. And you can figure that out if you go to Azure portal and look for the tenant properties. Then right? And then it is time to connect to the workspace that we have just created. And you can either use a predefined configuration file, or you can specify it by defining the name of the workspace, the subscription ID, and the name of the resource group. And yes, the subscription ID can also be fine if you just look for the subscriptions, and there you can find your identifier as well. And if the connection was successful, then it is going to return the details of your of the workspace. And then the next step is to create a new experiment, which will enable us to monitor the run. And as parameters, we pass the workspace that we just connected to. And we should specify also a name for the experiment, which is going to be particle multi-agent. And now we also create a cluster where the training is going to run. And first we define a name for it. And then we are going to look around for whether there is a cluster already that exists. And if it is, then it's going to say, yay, I found the cluster, so I'm going to use it. And if it exists, but stopped or not available, this code will also return that information. Otherwise, if it's not generated yet, it will be done now. We should also specify the size, the number of nodes. And you can always change this code to use an existing cluster. For that, you need to change the name only up here, which cluster you want to use. And the good thing about this cluster is that it will scale down when it's not used. And so you are welcome to increase the nodes as well if you plan to run more than one experiment on this cluster. And when the cluster is ready to use, this code will return the cluster created message. So we're going to use a customized Docker image where all the necessary software and Python packages are installed. And the configuration for the training run is defined with this environment class. And since we also want videos to be captured and displayed as results about the different runs of the particles, we need to set this interpreter path too. All right. Then for training, we're going to use the multi-agent deep deterministic policy gradient algorithm. And as the name suggests, it will be able to train many agents in the same time. So if the training runs over 3 hours, it will automatically stop. Similarly, if -400 as a reward is given. And we have to initialize reinforcement learning estimator with different parameters. So for example, the source directory where we put some files that is used by our solution. We also want to add what is the entry script, some parameters like what is the scenario we're going to use, and we use this simple spread scenario. We also pass the compute target and the environment that we have just generated. And you are welcome to change the final reward parameter as well. But this code means that when it is reached by the agent, the training is over. And the -400 returns with a pretty good result. But if you want it to be better, training might take a bit longer. And okay, you could also see, I know you can't really see it, but I can just highlight it for you. There we go. So you can see that the solution keeps improving. Now we could see more details about the run, whether the experiment is queued or already running or it's completed, the start time, the duration, and so on. And finally, if you also want to see the more information when the experiment is running, the link is available down here where we can review all this. And this is all gathered by running this part of the code, which is using the Azure Machine Learning SDK's run details widget. So if we go to the details and we look at the child runs, we start up this one, and then we go to outputs and logs. You can find a lot of detailed information about our run. And you can see from the beginning to the end, each and every iteration is written down, how long did it take, and what is the reward at this iteration. And as we are going forward in time, at some point we see -446, and then at some point we drop down to -400. I'm just going to scroll a bit faster, and then it's -400 in the end. Okay. The evaluation of a training is really important, and it is possible to show videos about the different iterations as the particles try to find their path without colliding. And the generated videos are saved in this logs folder. We go to videos, and maybe I look at one in the beginning. And sadly, we cannot watch it in here, but I can just download it. And this is their first try. They're not that good in it, right? No, they're not very good at it. So we start up a bit later one, maybe this one. Yeah, no, now look at that. Look at that, they're getting there, right? And then maybe the last one, the final one at minus 400. And that's just, wow, look at that. They're so good, right? Okay, I actually wanted to show you a lot of more cool stuff, but the rapid development of the SDK and tools used by this project, some parts of it are under reconstruction. But you can read more in my blog post, where I can also show that you could see the Tensorboard, where you can see you know, information about all the iterations while your experiment is running. And you can follow how the training process performs. And what I really like is that all the videos could be seen continuously within the notebook. So let's hope that these improvements and fixes are going to happen soon, so you can also go ahead and see these awesome things that this provides. And as you can see, you can use once again, so when you use reinforcement learning in Azure Machine Learning, you can easily monitor each iterations and see all the training results live while the experiment is running. So, and your journey in reinforcement learning doesn't need to stop here. If you want to read more, see the following resources: blog posts, articles, and code samples from the engineers of Project Paidia. So I want to thank you for your attention. I hope you find this session beneficial when you build your next game. I really can't wait to see what you come up with next. If you want to try out the project that we shown today, feel free to let us know in the chat so we can share more resources with you. And I want to say thank you again for having us at AI and Machine Learning Conference. Thank you.